Before we start just using the law of sines, let's take a moment to see where it comes from. There's two reasons for doing this. Not that you're going to have to show me where it comes from, but seeing that it does come from somewhere may help you to remember the formula. It may also help you to appreciate the fact that this isn't a rule that somebody came up with and forced to work in nature. Instead, it's a rule that people came up with when they observed things that happened over and over and over. So, thousands of years of mathematicians studying and learning went into developing the laws and the theorems that you study. So when we look at the law of sines, we can see that it's a fairly, at least from our perspective, a fairly easy derivation. You need to start with an oblique triangle. We have an acute oblique triangle here, and we have an obtuse one over here. And it doesn't matter which one you use. I'm going to use the acute triangle, but I'll show you that it doesn't matter if you use the obtuse triangle, you will get the same result. The first thing we need to do is make sure that we label our triangle correctly. If we call this triangle ABC, then we want to label the opposite side with the same letter as the opposite angle. So if this is angle C, the side opposite of that is side C. This is angle A, the side opposite is side B. Same thing happens in our obtuse triangle over here. The side opposite angle A is side A, and so forth. Even though it's not a right triangle, we label it in that same convention. Obviously, C is not a right triangle or a right angle like it typically was when we solved right triangles. So once we have it labeled correctly, the next thing we want to do is drop a perpendicular from one of the angles to the opposite side. It doesn't matter which angle you chose. This one, the most convenient angle to choose was angle B. If we do that on the obtuse triangle, then it looks more like this. The perpendicular falls outside the triangle, so you have to extend this side of your triangle AC so that it comes out here. In either case, you get two right triangles. If we look at the obtuse triangle, we have a small right triangle that's outside the main triangle that we started with. And then we have a large right triangle that includes not only the obtuse triangle we started with, but also the smaller one. But it's a big right triangle. Look at the acute triangle, which we're going to use in our derivation. When you drop that perpendicular, you have a right triangle right here, ABD, and you have another right triangle that's BDC right here. In either case, the perpendicular that we dropped is the height of the triangle. Now that we have right triangles, we can work with them to write the trig ratios. We can use Pythagorean theorem, or we can use the trig ratios. We're going to use the trig ratios, and I'm going to start with angle A. So I can say that the sine of angle A is equal to opposite, which is H, over hypotenuse, which is C. You know that's the hypotenuse because it's opposite the right angle right there. So sine A is equal to H over C. If I solve that for the height, then I multiply both sides by C, and I get C times sine A is equal to H. Now I want to repeat that process in this other right triangle that I have, and I'm looking at angle C. So I can write the sine of angle C is equal to opposite, and I have to stay inside this right triangle, opposite, which is H, over hypotenuse, which is opposite the right angle there, or A. So sine C is equal to H over A. If I solve that for H, then I multiply both sides by A, and I get A sine C is equal to H. Now if you look at our acute triangle here, then H is the same length, both in the small right triangle that's on the left and the larger right triangle that's on the right. So this H right here is equivalent to this H over here. So I'm going to set their expressions equal to each other. If I do that, then it looks like C sine angle A is equal to A sine of angle C. Remember that the angle A is stuck to that sine and the angle C is stuck to that sine. Together they make an expression, so they can't be separated except by an identity or an inverse, which we're not interested in doing right now. What I want to do is rewrite this equation right here as a proportion. So I'm going to divide both sides by the sides AC. And when I do that, the C's are going to cancel here, and I get sine of angle A is to A, as here the A's are going to cancel, so I get sine of angle C is to side C. Notice the angles are in capital letters, the sides are in lowercase letter. So this is the law of sines. Now if we rearranged our drawing up here and we drew our perpendicular from a different letter, then we would find another piece to this law of sines. There are 3 pieces to it. And we would go through that same process, and we would find that the sine of angle B is to side B, like that. So there are 3 pieces to the law of sines. You're only going to use 2 pieces at a time. So all of this needs to be in your notes. This is the law of sines. But you'll see in our examples that you may use sine A is to, or sine angle A is to side A, as sine B is to side B. And those are the only 2 pieces that you would use. You would not use all 3 pieces together at the same time. Now keep in mind that this is a proportion. A fraction equals a fraction equals a fraction. So all the rules of proportions are going to be satisfied here. So instead of having sine angles on top and sides on the bottom, you can flip the entire equation if that suits your purposes better. So I could say that side A is to sine A, as side C is to sine C, as side B is to sine B. But I have to flip the whole thing. I can't flip one fraction and not the other. The other thing you can do is a quick switch. This numerator can go to this denominator, and that denominator can go to that numerator. And all of those rules for proportions will work. Anything that's illegal for proportions is illegal for the law of sines. Usually this one is pretty easy to remember, so good luck with it. Let's look at some examples next.